Okay, so a random variable is any variable that gets its value from a random phenomenon, like a coin flip or the roll of a dice, or a random phenomenon like the mean value from a survey or the mean value from an experiment. So you guys have all done a BioWare, right?
Well,
You've you've collected all your data, right? For a BioWare, except Izzy.
oh, and I finally got a p-value of like 0.0007%. So really my data means something. And
Um, so Your, there is some level of randomness to whatever you did, like growing a plant or something, correct?
in mind,
Yes, yes, there is some level of randomness. The Your very low probability indicates that the amount of randomness is different enough that there's a very high chance that this was not just randomness, the difference. But within your data, each one grew differently, correct?
yeah.
And that's and if you treated them all the same, that is randomness. So meaning the mean of, say, each one of your things is random. It's a random variable. Okay? That's what it means to be a random variable. Any variable that gets its value through some sort of random phenomenon. Okay? Like, so you're doing a volume of revolution and Devin got his bounds. Those were not random. So or his area between his curves. No, those were not random. Those were picked at the endpoints of where the graphs met, or at the endpoints. That makes sense? So most variables you've dealt with have not been random variables. However, when you start collecting data, most things become random variables. Okay. If you randomized which seed was which for growing a plant, or you randomized who was in which group, your mean is a random variable. Okay, because there was randomization used in determining who was where and how those values came about. Okay. A discrete random variable is a random variable that takes on discrete values like 1, 2, 3, 4. Okay. A continuous random variable means it takes all possible values within the real numbers within some range. Random variable between 0 and 1. There is no limitation to how many decimal points it can have.
What's the difference?
Discrete, like discrete numbers, 0, 1, 2, 3, 4, A, B, C. One of the keys to the definition is, so what we're going to use is a table, kind of like this. Each value and its probability. Like all probabilities, they must be between 0 and 1. So the example of a discrete random variable is an instructor of a large class gives 15% A's and D's, 30% B's and C's, and 10% F's. Grade for GPA being 0, 1, 2, 3, 4. And we have the probability. This is a probability distribution for this random variable. Each student will not exactly randomly be assigned, but be assigned one of those, and it is a somewhat random phenomenon. Okay, who's going to score where? That makes sense. It's not just, hey, let's flip a coin. Where do you fall? You're gonna roll a dice. Oh, well, then I'd probably assign them 1 through 5 or something like that. Let's just roll a dice for who gets which grade. We're gonna do weighted grades.
No,
A weighted die.
so chicken.
Just just choose random. So this would be, do you guys remember Benford's law? If the random variable, remember that was the probability of the first digit in large data, and it was more likely to be one, right? So this is the random variable. If they're equally likely, this is if they follow Benford's law. All data, if it's generated correctly, is going to operate like a random variable. Okay. Okay, what is the probability distribution of a discrete random variable x that counts the number of heads in 4 tosses of a coin? We can derive this distribution if we make two reasonable assumptions. The coin is balanced, so each is equally likely, heads or tails. The coin has no memory, so tosses are independent. Do those seem generally reasonable? Yes. So we have this distribution, and I can write it out with probabilities like this. So this is the brute force method of getting them all. 1 out of 16, 4 out of 16, 6 out of 16, 4 out of 16, 1 out of 16, which shows up here. You can graph it, it looks like this. What? It's perfectly symmetrical. What is the approximate shape of this?
Okay.
It's a bell curve. It's a normal bell curve. Okay. Continuous random variables could be something like the spinner, but we're not just going with the nearest one. We're giving it the actual proportion. Okay, they're not zoned off. It's fully continuous. It's not Wheel of Fortune where you've got, oh, now you're from here, now you're in this one. So, random numbers in a uniform distribution. The random number generator will spread out its output uniformly across the entire interval from 0 to 1. We will allow it to generate a long sequence of numbers. The results of many trials are represented by the density curve below. So these are the density curves. So it asks me the probability between 0.3 and 0.7. It doesn't matter if it's an or equals or not. The probability of any value in a continuous distribution is 0. The probability of exactly 0.3 in a continuous distribution, because it's infinite possibilities. The probability of 0.3 with, essentially infinite zeros behind it is 0. So it doesn't matter if they say if they have the or equals or not. It could be this. Same thing. Still equal to 0.4. And because this is 0 to 1, we're just really considering the area. Does that make sense? It's like, hopefully this is pretty simple so far. The probability that x is less than 0.5 or greater than 0.8 is 0.5 plus 0.2 or 0.7. Again, we're effectively just considering the area. Any questions so far? In something like this, or what we're mostly going to look at is normal distributions. Again, it's the area. And you guys remember doing some of this with z-scores, correct? Finding different areas. That's where we'll effectively be doing this. But it works on any distribution. If you were doing calculus-based statistics and you had the formula for this, you could just do an integral. Okay. You do not have to do calculus-based statistics in this course. No, if it were on your IB test, I would teach it in this course.
Yay.
If I don't teach it in this course, it is not on your IB test.
It's 126, 126.
Yes, it is.
Be pretty.
So, the probability distribution of a density curve is described by the areas on a continuous. So, drugs in school. No drugs in school.
Don't look at me, Ted.
An opinion poll asks an SRS of 1,500 American adults what they consider to be the most serious problem facing our schools. This was probably done in the 90s. Suppose that we could ask all adults this question. 30% would say drugs. So we're making some supposings a lot in this next few sections. Okay? Because we're not quite there to do that. It says, we will learn in chapter 9 that the proportion is 0.3. It is a population parameter and that the proportion p hat of the sample who answers drugs is a statistic. So we're supposing that the probability actually is 0.3. We want to know if we conducted our SRS, what the probability of being off by more than essentially 0.2 is. Okay? They give us this information. Who remembers what that means?
That's.
Normal distribution.
Standard deviation.
It's a normal distribution with mean 0.3, standard deviation 0.118. Okay? So it says, what is the probability that poll will differ from the truth by 2 percentage points? So 2 percentage points being between more than less than 0.28 or more than 0.32. Again, and we don't really consider the endpoints on this. They don't matter because they each have a probability of 0. No, we're not rounding the standard deviation. It wants to know what's the probability that our sample, it's actually 0.3. What's the probability that our sample gets further away than 2 percentage points? It asks, that's part of the question. Okay. You'll at a later date learn how to calculate that. Okay. Later date, like end of this week, beginning of next week.
Wow.
No, I think it's either Thursday or Monday. Tomorrow you have a test.
Oh.
So, what are we gonna do? We're gonna do our z-scores. Okay. And you guys remember z-score being x minus x bar over s, or I guess you guys did it x minus mu over sigma. Um,
Not, not a big way.
so x bar and s just mean from my sample. So we get, you calculate that, you get negative 1.69. You guys remember going to your z table and looking that up and getting 0.0445? When you do the positive case, you get the positive and you get the same area. Amazing, it's symmetrical. Who would have thought that the normal distribution was symmetrical? So what's the probability of more than 2? 9.1%. Not super likely, but will happen with just randomly, even choosing 1,500 for my sample size. Okay. So yes, large sample size does not mean there is still randomness, but it was not a pretty low percentage for only 2 percentage points because of my large sample size. Does that make sense? Okay. So weighted average. I think that must be in 7.2. So a weighted average, instead of adding them up and dividing by the total, multiplies by the probability. So you guys know the pick three for the lottery? You pick three numbers. If you get them right, you win $500. You pay $1 for the ticket, or at least this is how it used to work. I think it still does. If you pay $1, you choose three numbers. If you get the three numbers right, you win. Now, I have,
What a question.
I think I participated in buying a couple of Mega Millions tickets when the was really high. Like teachers at my pool schooled and they're like, everybody want to put in like $2, and if we win, we'll split it all. We did not win. I think my dad has bought like four Powerball tickets in his life. He only buys them when the jackpot gets over 100 million. Like, what the heck? Somebody's got to win one of these days.
It taxes.
When it's 100 million, you still have 25 million left. But you obviously do not want to do the just average. Oh, the average you get is $250. No. 99.9% of the time in this, you get zero. 0.1% of the time, you get $500. So to average them, you take the value times the percent, and you add them together. and this gets 50 cents.
So what's like the formula for weighted mean?
The value times the probability of that value for each one and add them up. So a regular mean actually does this, it just assumes equal probability. So if you have, two numbers that you're adding, you would usually just call it like this, but it's the same thing as multiplying each one by half. Okay? The standard deviation would be much, much more complicated version of this. Okay, you will not do this by hand. You will not do the standard deviation by hand. Your calculator can do it for you. You're going to learn about that Wednesday, effectively.
Sounds like I'm getting very, very expensive.
Probably not. It's okay. If you don't get them right, it makes me look better when you do get them right on the next test.
Yeah, the same case for these.
So,
Yeah.
no, you only get one shot at that. So,
$200 a class?
you can just take them again, but yeah, then you have to remember.
I don't remember the first one.
Yeah. Yeah. So, the expected value is effectively the mean. Okay? You're going to hear that term, what's the expected value? You give the mean. The variance. Okay. Selling aircraft. So, they they showed calculating it by hand for the expected value or the mean. Calculating the variance is pain in the butt. So we're going to enter those four into a calculator. You guys got your calculators. Enter units sold into one and probability into the other in a table in your list of spreadsheets. To know how to do this? Yeah, it would have been nice if we could have gotten through everything before the IA, but they're due.
I these two then. Yeah. Cause like, no, like I these two then.
1,000, 3,000. 1,000, 3,000, 5,000, 10,000. I think it's 0.1, 0.3, 0.4, 0.2. I'm gonna double check that. Yes. Okay. So, do you guys remember how you find means and standard deviations, period? Add a calculator. Menu. Statistics. It, it overclicked on me. 6, 1. Nope. Menu. 6, 1. Stat calculations. One variable statistics. Number of lists, 1. 1. Choose 1. US is units sold. Your frequency list is PR, or probability. This is usually you use 1 if they're all equal. So what you're still doing it on one list, you're just changing, and I've tried the 2 lists. I don't, it comes out weird. So I just do one list at a time always, but one variable, or I've tried 2 variable statistics, and I think it does weird things with it. I don't think it does one variable twice. You could do multiple lists, but okay. Your mean, 5,000. Your standard deviation. Um, your standard deviation notice is normally SX. When you do a probability list for a weighted, it is sigma X. Okay. So when we're having probabilities here, if probabilities are involved, it's sigma X. It's normally it would be the SX one. But if everything's equally likely, it's SX. If everything is not equally likely, then it's sigma X. My standard deviation here is 2,792. Fairly big standard deviation. Does that make sense? That wasn't so hard, was it? It's remembering and it's the abstractness of where we're going with random variables and things. Okay? So, couple of important things. The law of large numbers. If you have a large enough data set with independent observations drawn at random from a population with finite mean mu, decide how accurately you would like to estimate mu. As the number of observations draws increases, the mean x bar of the observed values eventually approach mu. So you flip a coin. It's supposed to be 50-50, right? No, the mean goes towards the expected mean.
Oh, wait, so,
The actual mean, what you actually get, approaches the theoretical.
and that's like the expected, it's like expected. Mean.
Mm-hmm.
So like with our, we said it's like how eventually sort of, to.
1/3, 1/3, one. Mm-hmm.
Gosh.
It's part of the exploration part. I was like, there isn't a great way to do this because ideally I'd love you to have every section done before you start your IA. In that case, you guys would write all your IAs at exactly the same time for every class, and I would have to grade them the day they're turned in so we could submit them to.
Yeah, it's like, the history hour was supposed to be done, but you find out most of those. Yeah. I thought. Spanish IA, you mean the test at the end of the. There's an IA for Spanish, the speaking one?
Yes.
Speaking one. That's at the end of the year. Well, that's in 2 months. Oh, no, we did get our English one done. It's the only good grade I got.
A four? Yes.
Not about a three in music.
Um, so law of large numbers, it approaches. Okay. The height of young women on average is 64.5. As they take more and more observations, it approaches closer. Um, the law of small numbers says you should expect some variation within small data sets. 10, 20, 30, 5. Okay. That it will vary somewhat around that mean, but you take a random group of 5 girls, there's going to there's a reasonable chance they won't have a mean all that close to 64.5.
So, like, in, sorry, smaller sample sizes expect variation between actual mean and the like predicted mean growth.
Hmm. In small sample sizes, you should expect that there will be some variation. Potentially significant variation too. So, have you guys ever heard of the hot hand for a basketball player or a
Devin, that's you.
I do not have that as a demo. It is so bad.
Because you don't practice or play, man. You went to one game and two practices.
No. That's a point.
God, man, more bonus.
no, that probably has a lot to do with it. So, basketball free throws are often used as an example of randomness with somebody is, let's say you're a 70% free throw shooter. You'll make 70% within a random distribution. Some days you'll make 90% of your free throws, some days you'll make 50. Okay? And is there potentially more to it than just absolute randomness? Yeah. No, no, no. Within LeBron James, so he shoots at say X percentage. So yes, him having the flu. Me shooting free throws, I do not repeat the exact same form every time. Okay. There is some legit variation that's maybe not randomness, but with a good basketball player, it's pretty close to can be simulated with randomness based on the overall percentage. Okay. So we're gonna do a lot of basketball free throws and things like that in the next week. Okay, and treating them as if they were random. Sorry, we're not going to go to the gym and practice our basketball free throws. Um,
Yeah.
so gambling is another example of the law of large numbers. In the law of small numbers, there are nights when the casinos don't do well. But over the course of a year and over years, they they do quite well because how much they pay out is based on these probabilities. Okay, that makes sense. So, what if I have multiple means? Or remember doing like shifts on a mean where we said everybody got an extra $100,000 for winning the NBA title, or everybody got a 10% bonus? Uh-huh. So, well, it does affect the mean. It affects the mean by the same amount. So, how we notate that is the mean transformed by a linear transformation or a scaling transformation. Okay? And we can just add the 100,000 or multiply the mean by 1.1. We don't have to recalculate it. Okay? if we have two means, if we're adding two sets of variables, so you get paid for your professional sports career and your endorsements, we can add the means separately. Okay? Does that kind of make sense? We'll go through an example in a second.
I think I just needed to practice.
That aren't letters. So, um, so this is the one we just did. If you add up their y, you get 445. Okay?
No, you can stay.
We're gonna skip over this one for now, and I'm gonna. So what they're doing effectively is they're taking, they're selling these, which averaged 5,000 at $2,000 a piece. So that means they're going to make $10 million off of those. They're selling these ones at varied prices. They average, or they sell them at $3,500 a piece.
What would be its context?
So this is cost. Mu sub x is the average of these. They think they'll on average sell 5,000. 3,500 is the cost. Mu sub y is the average for these. X and Y are random variables. They don't know how many they're going to sell, do they? But they have this distribution that predicts it. Okay. So they can take 2,000 times their predicted average X and 3,500 times their predicted average Y to estimate their profit. And they're kind of doing we're doing the multiplication kind of weird. So they kind of plug those together. So they're going mu of 2,000x or 2,000 times mu sub x.
A and B.
That's the sale prices. No, those are B and B. Those are two separate ones. So looking at your previous notation, B is the price. They're both B's. There is no A in this case. It's B for two separate variables, and then to get the overall average, they added those together. Pretty much, yes. It's not going to be when we do standard deviation. Okay.
No, I never feel.
Okay,
Hey,
so we're talking, do you remember that standard deviation squared is called variance?
Yeah.
Coleman's totally got that one down. Even though he doesn't know what standard deviation is.
Wait, variance was the thing that we were calculating with it. Right?
No, well, you got standard deviation.
Wait, no, but it was like a fine variance.
Yes, but your calculator gives you the standard deviation, so if you want variance, you square the standard deviation. You take your standard deviation value and you square it. No, sigma squared. So that's where the sigma squared thing is. And all of these rules you do to variances, not to standard deviations. What does it do? It's literally the standard deviation squared. Why? Well, when you calculate the variance and then you square root it to get the standard deviation.
No, wait. That seems very bad.
so it's just like another way of measuring.
It's a spread. So literally, when you go through the standard deviation formula, you take each value minus the mean, you square it, you add them all together. That's the variance. Oh no, then you divide by n minus 1. That's the variance. Then you square root that and you get the standard deviation.
Okay. My calculator is gonna do all that for me.
Your calculator does all that for you. Okay?
Here.
Getting the variance is literally just a part of the standard deviation, but you cannot add standard deviations. You can, however, add variances.
What? Variance of constant.
How does all these statements?
Because it doesn't work. I was like, I'm sure there is some much better mathematical proof of it. I have never done proofs on statistics.
It's like,
Probably good for my sanity. You're the why, I don't know. You guys remember that when we did a linear shift, it did not affect the spread, correct? So like the adding $100,000 has no impact on the standard deviation or the variance. However, when we did like a 1.1, we have to square that if you have a scale factor. More like a effect of $2,000 per unit sold, you'd have to square the 2,000 when you multiply by the standard deviation. Or by the variance, actually, the standard deviation squared. Okay?
what are you nodding at? It's not.
Does that make sense? Notice that whether I'm adding or subtracting two random variables, I add for the variance. I add the variances, period. Whether it's plus or minus that x or y.
What is it? Okay. What's the word? It sounds like so. It's like. Oh.
It's kind of like Pythagorean theorem, essentially. That is a very, very vague, non-descriptive way of, or non-specific way of saying that. That will not qualify as a proof. Okay, does this make sense so far? But notice there's an if condition on the second one. Good news for you, I do not think does any that are not independent. Okay? I do not think you have to know this next case, but I'm going to show it to you. If they are not independent, that means they have a correlation value. Usually we call that R. Okay? It's effectively the same process. It's kind of like love, sines and cosines. But then you have to do 2R, and then you multiply the two. R, correlation. Remember, it's a row, yes. They're giving it a correlation coefficient of rho instead of R. I don't know why.
What? You didn't. Now I got one more month. Be a silly fellow.
Okay. So let's do some examples with this, and then we're done. So, investing in stocks and T-bills.
Stocks.
Okay. Zadie has invested 20% of her funds in treasury bills and 80% in an index fund that represents all US stocks. The rate of return of investment over time period is the percent change in price during the time period plus any income received. If X is the annual return on T values and Y is the annual return on stocks, the portfolio rate of return is R.2X plus 0.8Y. That makes sense? Okay. Now, treasury bills, on average, return a 5.2% yield with a standard deviation of 2.9%. Okay, and stocks return 13.3% with a standard deviation of 17%. So, for the return, Zadie can expect mean 0.2 times 5.2, 0.8 times 13.3, or 11.68% return on average. Notice they also gave this for a correlation. So, for her standard deviation, okay? Notice the 0.2 and the 0.8s there. What does that mean? 0.2 times sigma squared x plus 0.8. Oops, I need to square those. 0.8 squared sigma squared y. This is a plus case. Plus 2 times rho. Notice these ones are not squared, so I am not squaring those. So that works out to be this, giving me a variance of 183.79 and a standard deviation of 13.55%.
I think you're right. No, darn.
Does that make sense how we used that formula? Where what it was squared, because this was only 20% of it, I had to square the 0.2. Because this was 80%, I had to square the 0.8. Whereas these ones not being squared, I did not square them. Okay. So combining random variables, a round of golf. So Tom and George are playing in a club golf tournament. Their scores vary as they play the course repeatedly. Tom has a score of X, makes a normal distribution, mean 110, standard deviation 10. George, better golfer, has mean 100, standard deviation 8. That doesn't mean that Tom will never beat George, because if Tom has a good day and George has a bad day, Tom's probably going to beat him, right? That makes sense?
Better in golf, right?
Low score is better, yes. So Tom averages 110, but one standard deviation below, which is like 16% of the time, he scores 100. George averages 100, but anytime he's over the mean, he's over 100. So Tom will beat him sometimes, but not that often. So what we're going to do is we're going to calculate the difference. The difference in the means is 10. Is Tom and George's score probably independent? Yes. So we get sigma squared of 164. That gives me sigma of 12.8. So I can use their comparative score as a normal distribution with mean 10, standard deviation 12.8. That makes sense? And I want to know when the comparative score is less than 0. If x minus y, George minus Tom's score is less than 0, that means George beats Tom. Okay? So what I have here is we're going to call it z minus 10 over 12.8 gives me, and z is 0 in this case, because I'm looking for when it's less than or equal to 0. Negative 0.78. And if I look that up in my z table, I get 21.77% of the time, George will beat Tom. You guys remember how to look things up in your z table? So yeah, don't focus too much on this x minus y part. Don't get lost in that. That's why I called it z. I'm looking for when is the difference less than 0. That is the entirety of chapter 7. You do have a test on chapters 5 and 6 tomorrow.